Hello and welcome everyone to our webinar that's offered jointly by the Mobilize Center and Restore Centers at Stanford University. My name is Matt Petrucci. I'm the Scientific Program Manager of both these centers, and I'm excited to serve as your moderator today. Today's speaker is James Cotton, who will share how his lab is advancing markerless motion capture using single and multi-view videos for clinical applications. The first part of the webinar will give an overview of his pipeline, how they compare to past approaches, and discuss the new opportunities that they have given rise to in clinical applications. In the second part of the webinar, he will lead an interactive tutorial on fitting biomechanics from a sample monocular video using an end-to-end optimization-based approach. Today's webinar is brought to you by the Mobilize Center and Restore Center, which are both supported by the National Institutes of Health. The Mobilize Center is focused on developing and disseminating state-of-the-art biomechanics and machine learning tools for researchers to analyze human movement. The Restore Center is working to make these and other tools for real-world assessment of movement more widely available to the rehab research community. Before we get started, a couple quick reminders about the format of the webinar. We will have a research talk and then a tutorial, and we'd love to take your questions from both. We'll take your questions at the end of the research talk and at the end of the tutorial. Please type your questions into the Q&A panel in Zoom and not the chat. One thing to note is this webinar will be recorded and posted to our YouTube channels. Now I'd like to introduce our speaker for today. Dr. James Cotton is an electrical engineer, neuroscientist, and physiatrist working as a physician scientist at Shirley AbilityLab and assistant professor in the Northwestern University Department of Physical Medicine and Rehabilitation. His lab works at the intersection of artificial intelligence, wearable sensors, computer vision, causal and biomechanical modeling, and novel technologies to monitor and improve rehabilitation outcomes. In particular, they focus on methods that can be easily translated and disseminated at scale into the clinic or real world. This includes biomechanical analysis using computer vision, which we can integrate into the clinic and establishing how this can be used to improve clinical outcomes. With that, we are excited to have you all here today. I know we're all excited to hear James speak about his research, so I will let him go ahead and begin.
Okay, I believe you can all see my main slides now, right? Wonderful. Okay, yes, so thanks for that great, kind introduction, and I'm happy to have this opportunity to talk to you about some of what we've been doing and hopefully get you to replicate some of it. And so, I'm really passionate about getting movement analysis out into the real world and out into the clinic. As a rehab physician, how someone moves tells us so much about their health status. And I just want to kind of highlight this through a couple of examples. And so if you look at this first person walking, you probably don't see any gait impairment, and you'd be correct. Now, if we contrast it to the second individual, you can see they've got a much slower cadence. It's asymmetrical. They're using a cane on the left. They've got kind of a stiff-knee gait swinging through on the right. And this is an individual with a stroke. And here's an individual with another stroke who's slightly less impaired and kind of with the asymmetrical kind of other side affected. And then this individual looks relatively unimpaired, but if you watch more closely at their trunk and arm symmetry, you can actually pick up a little bit of an asymmetry, and this is a transfemoral amputee using a prosthesis. And then finally, this last example is someone with a spinal cord injury using a rolling walker. They've got adductor tone. You can see that kind of scissoring like that. And so obviously this tells us a lot about health, but the problem is in rehabilitation, we don't measure these things. And I really liken this to, imagine if cardiology didn't have access to EKGs and MRIs and things like that, and they only got to use a stopwatch to measure the pulse, we wouldn't have the kind of clinical outcomes that we do right now. And that's where we are in rehabilitation in some respects. And I think a big part of that is because we don't have the tools that make it practical to actually measure movement in the real world. And then, of course, if we do have those tools, we still wouldn't necessarily have the analytics to produce easy and meaningful metrics. And so towards that, we've been integrating cameras into our hospital. So here's one of our therapy gyms. I think you should see my mouse cursor. And you can see along the roof, there's a row of cameras. And then this system is collected with this laptop that can just be kind of set up in this closet out here. And we can collect multi-camera video. I'm not going to talk about all the details of our methodology, but here you can see just some of our works that we've been doing over the years, including with collaboration with the Restore Center back in the day, and developing multi-camera systems. This is a screenshot of our acquisition software. This is kind of how it tracks some of the recordings within a session, which we then push to a database. I'm not talking about our infrastructure here, but there's a lot of core infrastructure that underlies all of this large scale data collection. Most of our people actually require assistance to walk. And so an important step is actually identifying who we're interested in studying versus who's a therapist. And so we have these relatively easy to use dashboards for annotating things like this. And then we get the biomechanics, which we'll be talking about in a moment. And we have dashboards that allow us to interact with that data, look at it in 3D. If I jump forward a little bit, just for time, you could see this is person a little bit later, and they've improved their cadence, their hip extension, things like that. And so I want to take a moment to kind of contrast the methods I'm going to be describing to more traditional methods. And so the history of biomechanics is often driven from marker-based, where these systems using infrared and filtering can really precisely track markers down to sub-millimeter precision. And then essentially, if you track a marker, you know exactly where it is. And then you take those trajectories that are triangulated, then you perform inverse kinematics on those, and then you may perform dynamics. Maybe you add ground reaction forces, EMG, things like that. But the pipeline is really treated as a series of separable stages. And that makes a lot of sense when you're doing marker-based analysis with these very precise markers that you track. It's not as sensible in the case of computer vision because there's a lot of noise in the detections from each camera. And what you really want to do is allow what you know about biomechanics to constrain that optimization. So if someone's limb length is something, that will really inform you where their joints should be or the combination of joints. And if you don't take that information into account when you're creating the trajectory and just naively triangulate, you're not going to do as well. And our papers have shown that. And so that's why we've been working on this end-to-end approach, where essentially we collect all these measurements, in this case, the computer vision detections, and we have a representation of the trajectory, and we optimize that with respect to the key points that we detect. And as we go through this optimization process of the trajectory, we get this nice alignment with the person. And you could see, here's just kind of a slightly different explanation of it, where the representation of our trajectory is essentially a neural network that is a mapping from time to joint angles. And in most cases, you'll think about training a neural network is to do downstream tasks. In this case, we train that neural network just to know this person's kinematics, and then we discard it. So it's a tool for the optimization process. And we can actually then fit that over we can have multiple of those trajectories for multiple trials with a single set of body scaling parameters. So that's going to include the anthropomorphic measurements as well as the marker offsets. And so this is actually very much like the Add Biomechanics paper with the bi-level optimization, where we jointly optimize kinematics and body scale, informed by all the data. We take those hypotheses, pass them through our biomechanical model. In this case, we're using MuJoCo for our physics simulator because it's GPU accelerated. We can massively parallelize and do this kind of gradient-based back propagation, which is really powerful for us. And then we kind of take that hypothesis, compare it against these key points, and then back propagate through that model. The end result is something that looks like this. And so, and I really like making these overlays. It's a good way to kind of know what's working and what's not working. And you can see here it's tracking this person quite nicely. And when we really go and quantify the performance, we can look, for example, at a number of spatial temporal gait parameters against an instrumented walkway for a large number of subjects in different clinical settings. And we see that typically most of our gait parameters are within 10 millimeters, sometimes 15 millimeters. I think a lot of the increase in the step length actually is because of the difference in the pressure distributions, whereas the computer vision, which is what the mat measures, whereas the computer vision looks at the actual geometry. When we actually compare our end-to-end approach on the vertical axis versus a two-stage approach using the Nimble Physics simulator, we see that all the points are above the axis, which shows that we find a more consistent reconstruction. And what's nice is because this is a big optimization problem, we can also put things in like the calibration of the cameras, and we actually see additional improvements from that. So while we do an initial calibration and take pains to make sure that's accurate, all that data we collect can actually inform a little bit of a refinement of it that seems to have some benefits. And so here's just an example of someone early and later in rehabilitation. And you can appreciate that they're walking more quickly. The therapist is actually applying less force. So sometimes the other things in the biomechanics actually tells you a lot. They've changed the assistive device they're using, and they've improved some of their gait kinematics. Here's another person, and we can kind of see similar things, and we can really go in then and look and see that, okay, this person has made their hip kinematics slightly more symmetrical. They've increased the range of motion. They've increased their knee flexion. They got a little bit more stance phase knee flexion on one side. So we can really pick up clinically interesting differences. Now, another thing that's really important for us is the ability to know when we can trust this. And so while what I've described before was actually getting point estimates of the trajectories, we can actually extend this format to produce a probability distribution over the joint angle trajectory. So, for example, you've got your elbow with an uncertainty around it and an ankle with an uncertainty, and these uncertainties actually change instantaneously for each joint and each moment in time. And basically, I won't belabor the math, but we're using something called variational inference to compute the likelihood of this and maximize the negative log likelihood. And a part of the details are actually learning the uncertainty from the key points, but we actually see that this does fairly well. So if we go, for example, and synthetically inject noise into the key point detectors, the fact that all these trials lay on the diagonal shows that we correctly identify the amount of noise in our computer vision, which again is much higher than the amount of noise you'd get in a marker-based system. Similarly, as we add noise, our uncertainty over our joint angles increases and our entropy over the distribution increases. And then conversely, as we add cameras, we become more confident in general. And while we're generally tracking quite well, even with fairly few cameras, what we actually we see is that there's still a lot of outliers, and the more cameras you have, the more you can reduce that. Critically, this allows us to distinguish two trials, such as this top session, where if you look at some of these joints in the lower limb, you can see that the confidence intervals are pretty stable. If this is the uncertainty from each of these joints, you can see these are fairly low. As we go to more distal joints where they're kind of shorter, we have the uncertainty go up in general, which is intuitive. But we can contrast this to another extreme trial like this, where at the edge of the room, it starts being occluded and it really doesn't know what's going on, and it correctly assesses that it doesn't know what's going on. So we're excited about this for large scale use of these technologies. It allows us to look at things like the 50th percentile, the 95th percentile distributions of errors over trials. And we see that we're typically tracking most body parts within, about 10 millimeters, which is similar to what we were seeing when we compared against our instrumented gait right. And similarly, most of our joints are tracking within a couple of degrees. So that's quite reassuring. What's also nice about this representation is we can actually extend it into the kinetics. And so what we can do is take that representation I described earlier, which is a mapping from time to joint angles. And because it's a function, we can take the derivative with respect to time. So now we have time going to joint angles and joint velocities. And we can augment that representation to output the actions at each point in time. And then because this is running in a biomechanics physics simulator, we can actually roll those physics rollouts out in time and actually make sure that where it ends in a few frames aligns with our detected key points. And so essentially, this is our end-to-end approach extended to kinetics, and you can think of it a little bit like direct shooting. It's got some interesting connections, I think, with MuJoCo as well. And what's nice about this is we're actually starting to see, first of all, if you just look at the vectors of the ground reaction forces, they look fairly plausible. But more excitingly, if we actually go and look at these waveforms, this is an individual with a stroke early in rehabilitation, and you can see they don't have too much knee extension during stance here or during swing. And the only torque you really see from that knee is a passive extension during stance. But later on in rehabilitation, you can see that they actually have a lot more knee flexion, and you can actually see more dynamics in the torques and this flexion moment that's actually allowing them to swing through. And similarly, if we look at the torques at the hip, we see a real increase in the power and symmetry there. So is this right? Absolutely not. We are not scaling masses. There's a lot of things or moments of inertia. There's a lot of details if we really wanted to get it like accurate at the level of what we'd get with a ground reaction force. But I'm more interested in can we pick up clinically meaningful changes? And this is looking quite promising. And of course, we really want to get this out in the real world. So a critical thing there is making sure that the data is usable by our end users. And so for that, I'm happy to work with Miriam Rafferty, and we're trying to create more and more dashboards that can handle all this data and visualize it. And so here is one that this after a couple of rounds of iteration, and you can see that we can, for example, plot the asymmetry of step time and step length and see how that reduces during inpatient rehabilitation for this participant. And so, a lot of work to do still, though. Now, I don't want to neglect the arms and hands, and so we've been working on that too. And so on the left, you're seeing some results where we compared the arm kinematics to marker-based motion capture, and this was this great data set this team in Switzerland had collected. And what we found is that our markerless system agreed with the marker-based system within a couple of degrees most of the time. Interestingly, if you really went in and analyzed the variability trial to trial, we actually saw more evidence of problems from the marker-based placement than we actually do with the markerless. So I think if you're looking at inter-session or intra-session comparisons, there's definitely some potential benefits of markerless. And then so you can see here, for example, that hand is kind of choked up. It's not quite tracking it correctly. But then Puyan Firabuzi has been doing some great work improving our ability to actually track down to the level of individual joints of the hand. And so we're typically now within a couple of millimeters. And you can see this is a set of cameras closer to the person. So we're excited about that. We can take that into the real world and do full body skeleton tracking, which you can see there's glitches on the end of the room, which is again why we need these probabilistic representations. But you can actually see some of the subtleties in how this person uses their hand. This individual has a cervical spinal cord injury, and you can see they don't have a complete grasp pattern. They're grasping more with the distal joints. Okay, but can we make this more accessible, right? This multi-camera system is quite powerful in our minds, but it wouldn't make for a very good workshop where you could do it your own demonstration. And so towards that, JD has been working on this, and some of the earlier version of this is in this preprint from or paper from last year, where actually he was looking at how well we could fuse sensor-based and computer vision data together, and he came up with a great algorithm for fusing it. But the takeaway was we get most of the accuracy from the computer vision unless there's occlusions, and then sensors add a lot of value. And so more recently, he's been pushing on this. Hopefully, stay tuned. The preprint should be out very shortly. I was hoping it would be out for this workshop, but sorry about that. And it will have better documented code than what you're about to see. But the short version is we have our smartphone platform, which you're seeing here. We tend to record people with a gimbal just to make the video smoother. And then similarly to what we described earlier, we're getting the 2D key points from that computer vision. We also are using an algorithm called Metrabs from this great guy, Istin Sarandi, that does a very good job of computing both 2D and 3D key points. I don't want to get too much into it, but this paper used a very clever approach to combine all the existing data sets with images and 3D data to produce a Rosetta Stone and map between them and really get high quality kinematics or 3D joint locations. And then because we have these 3D joint locations, we can fit our models to those. And here we're essentially minimizing both the reprojection loss to the camera with, like, if you have the camera intrinsics, you can take those into account. And we actually take into account the sensor data from the phones as well, so we can separate the rotation of the phone from the rotation of the person. And the end result is something that looks like this. So here you're seeing this individual walking. Notice as that camera pans, it's still tracking the person stably in 3D space. And so you can see that the positions are tracked pretty well. If you don't have sensor data, there's also ways you can do this with simultaneous localization and mapping that works pretty well, but not quite as well in our hands right now. What's nice with this system is it tracks quite nicely. So here you're seeing a couple of a couple of examples of a control participant, someone with a neurologic gait condition, and someone who uses a lower limb prosthesis. And when we compare the multi-camera system to the single camera system, we see quite strong agreement. And when we look at that error with respect to most joints, we see most joints are below 5 degrees most of the time. There are some viewpoint dependent things, but I'm not going to belabor these points. In short, it's robust across activities, clinical populations, and across joints. And what's nice about this is it's very easy to disseminate. And so, like, for example, on the left, this is a collaboration we have with a neurosurgeon at St. Louis, Dr. Pennycook, and he wanted to look at gait outcomes pre and post cervical myelopathy decompression. So now we could really recruit easily when we take that data collection to his clinic. Similarly, on the right, this is a collaboration with the Northwestern Human Longevity Lab. And so this technology is really improving our ability to collaborate. And what's nice is we're seeing it sensitive to clinically meaningful differences. And so here, we're looking at something called the gait deviation index. And so this is a holistic measure of gait quality. We're using actually a large normative data set we collected at the Society for Biomechanics meeting last year that hopefully we'll put out in not too long. And there we can actually compare the gait deviation index. And when we look at people who use prostheses, as we go from a transtibial to a transfemoral, there's a kind of, it's sensitive to those clinical differences. If we look at inpatients who had the Berg balance scale performed, which is a measure of stability, we see that it's also stratifying people based on their GDI. And when we go and look at the modified Japanese Orthopedic Association score, which is a self-reported outcome used in cervical myelopathy decompression, or cervical myelopathy in general, we can see it's sensitive to those changes too. And we can even put this on an autonomous drone that's following people, and we can reconstruct biomechanics out in the real world. So that's pretty fun. And so this is all enabling big rehabilitation data, but what can we do with this, right? And I don't want to go too much into these things. I could talk about this for another hour, but we want to make sure there's time for the workbook. So I'm just going to show you briefly some recent preprints. preprints. And so one of them is using imitation learning. We can train what's called a policy that is a decision-making rule that if you have a simulation and you have the current state of your model, and then you have some future observations of what you're meant to do, what are the forces you should apply to that model to replicate that? And again, we're doing this in MuJoCo where we can do really high speed, massively parallelized reinforcement learning. And what's nice about this is it produces essentially a kinetic twin based on observing someone's kinematics. And we find that the tracking accuracy of our system is really quite good. We're tracking within a couple of degrees for most of the joints. Speed is quite good. Now, there's details we need to tune up with some of the ground contact interactions, but I'm excited about this because we've seen, especially from smartphone in the past, that when we put these physics models into the inference process, it can really improve our accuracy. And sorry, advance. And for example, when we look at this in a prosthesis user, we can pick up things like asymmetries in the propulsion from their prosthetic side on the left compared to the much greater anterior propulsion force on their intact side. And when we look at things like where the physics predicts the center of pressure compared to the instrumented walkway, you can see it's also doing quite nicely. When we look at, for example, the same transfemoral amputee on different days, we get fairly consistent results, versus if we look at a control, we also get fairly consistent results. So starting to have some signs of face validity, although I'm not going to pretend there's not a lot of work to validate it. And going even more into things that need validation, we can even do this with a musculoskeletal model that is learning how to then replicate the movements it's seeing based on muscle activation. So this is slowed down basically because the simulator runs a lot faster than the video frame rate. But critically here, you can see we pick up asymmetries in the muscle activation firings that definitely make sense based on this person's impairment. And we also see differences, asymmetries in the propulsive from their impaired side. So check that paper out if you're interested in it. Another thing we've been working on is we have this bit of problem now that as we're making it easier and easier for us to collect data at scale, it's harder and harder for us to keep up with all the questions people have. And so one of the questions we've been asking is, can we train a language model to be able to help with these tasks? And I think I want to kind of take a brief moment to touch on whenever you're talking about language models and AI, particularly in healthcare, I think it's really important not to anthropomorphize them and treat them as like artificial human level intelligence and just assume they can do things, but rather to say, what are the specific things you want to do and can they do those and what are the performance metrics? So in this paper, we went and really said, okay, what are a number of tasks that we have data on that we would like our multimodal model that understands biomechanics to do? And we had things like identifying activities, identifying if someone has an impairment, what their diagnosis is, if they're using assistive devices. You can see the rest of the task here. Most of these, we had a lot of trials, a fair number of participants, but some of them fewer in the test set. And then we can create essentially a way to tokenize movement so that they're essentially, you can imagine action sentences, and we can treat those as a foreign language for a large language model that's pre-trained and train it to be fluent in this additional language. So you might give it, for example, action sentence, what is this person doing? And then it will answer walking. And so let me just kind of make that clearer by showing a video of it working. And here you can see, you ask what it's doing. The person's overground walking. Ask, do they have a gait impairment? It says yes. You can ask, what is the likely diagnosis? It correctly identifies amputee. In the next question, it will get wrong. So we ask it, what is the assistive device they're using? And they are using, it says a forearm crutch, but in this case, it was a cane. So we're pretty excited about this. The next, I won't wait to the next one, but it's going to look at some timed up and go, I think. But as I said, it's important to really score the performance on these things. And we see that the F1 score for activity classification is quite high, even in the case where there's some activities that we don't have frequently, take the L test. Or it can do a pretty good job of identifying a diagnosis if someone does have an impairment. It does a really good job of detecting if they have an impairment. That's like 88%. And that's across a diversity of activities, right? So we've previously done this with contrastive learning in just walking, but this system can kind of learn from a bunch of things. We find it actually outperforms things like XGBoost, which are often used for classifying these sort of things. And really excitingly, it's kind of a detail within this table, but if we only train on 2 activities, activity and recognition and identifying gait impairment, we find it doesn't do as well as when we add in additional tasks. And this is what's called positive transfer learning. So as we add more and more question tasks to what we train the system to do, we see that the performance on the original set of tasks actually continues to improve. And so this is really promising because that just means as we keep adding more and more things to it, we hopefully deepen its understanding of human movement, and then it can start solving more and more tasks with less and less data. But I think it's an important question to ask, like, is this the right tool for all tasks? And I think, we struggle with this a little bit because you take these raw biomechanics, which have a lot of these details in it, and then you kind of create this new representation and this new language, and you teach a language model to work with it. When is that the right thing to do and when is it not? And I think, one of the other things you might want to do is actually write code. And so this is another system we've been playing around with where we actually train a language model to actually, you can ask it, well, sorry, we don't train actually, this is just kind of a prompting. But then, and what's nice is because all of our infrastructure is in a database and it's well formatted and annotated, it can really go in there, it can explore the data. Sorry about the formatting on this, but it can make plots, it can pull up those kinematics of people moving. It can use some of the tools we created. And so it can use like Biomech GPT, it can use KinTwin. Here it is looking at the cadence. Again, it's pulling up the visualization. Sorry, this is sped up a little bit. Next, I'll ask it to get the ground reaction forces, and it will make those plots. And what's nice is it's actually all running on an on-premises language model, which is good for any kind of security concerns or privacy concerns. And they're the vertical ground reaction forces that it was asked for. And what's nice is then we can also start to fine tune this to kind of combine it with Biomech GPT and this kind of code reasoning agent. And finally, I just want to thank everyone in my lab that has helped this happen, all our collaborators, all our funding sources, including the NIH and the NIH through the Restore Center, who gave me some funding a couple of years ago. And I think we have a Q&A session, and then we'll move on to the workbook.
Great. Yeah. Thanks so much, James, James, for a super clear talk. And now we'll go ahead and start the Q&A, as he mentioned. So again, if you have questions, please go ahead and type those into the Q&A panel, and we'll get to as many questions as we can. So just looking into what questions have come in. I think you mentioned this, but just Bradley Scott had a question. And what is the average joint angle error in degrees? I think it was around 5 degrees in the.
Yeah, it's so let me pull up the figure. So it's I should have not unshared my screen. So
Yeah.
this is the figure that will be coming out very shortly. And you can see that this dotted line here is 5 degrees. So our median errors in the legs, for example, across all these populations are always under 5 degrees, other than right here, the ankle is right around 5 degrees in the pediatric population. But importantly, see there's those confidence in those bars around it, right? So sometimes we do better, sometimes we do worse. One thing we don't have as well for the single cameras we do for the multi-camera is that kind of that way to know when it's trustworthy and when it's not. So we're working on that. We have a paper a couple of years ago called Platypose using diffusion models where you can really draw multiple samples. And so we need to get that working with the biomechanics. So we have a pathway to that. But yeah, in general, you can see also, we also compared this to the MOVI data set, so a marker-based data set. And there too, we see our errors are below 5, our median errors are pretty much always below 5 degrees across the body.
And Helen Gravestock is the next question. I guess, is it on this plot in terms of how big are differences in asymmetries in knee and ankle kinematics, or did you measure that?
Well, I mean, that's going to very much depend on the person, right? So we haven't done population level analyses, but maybe I'm not understanding the question right, but some people don't have much of an asymmetry, some people do. And, we cannot, going back to this, like, for example, we could see in this case, this person improved, and they actually improved quite quickly. This is only 6 days, but their asymmetry reduced quite nicely from, 20, or I think, shoot, I'm forgetting the metric I was using too. There's a slightly different version of the symmetry index that's well normalized between 0 and 100% that I used here.
Yep. The next question is from Ruse Dune. Which type of musculoskeletal model are you currently using in your research? And then do you think that population-specific models, such as male, female, or pediatric models, would improve the accuracy of your?
Yeah, so there's 2 models we're using right now. Most of the work I showed you today and what you'll be using in the notebook is this MuJoCo model, which is derived from the Hamner model in 2010. And in that one, we don't have any kind of like a sex-specific model. then when we go to the whole body tracking, we're using the MyoSuite's myoskeleton model. That one has 150 degrees of freedom, including full articulation of the hands on both sides. And we don't see, it is in that 2024 paper on differentiable biomechanics. We don't see a big difference in the gait parameters, at least between those two methods. In terms of, so I'm probably not the right person to ask about sex-specific models. I mean, there's definitely differences, right? But like whether you can, so our system does allow the pelvis to scale, and whether that's sufficient to capture things, I don't know. I think it would depend on the question, to be honest.
Definitely. Let's see. Oh, Bradley Scott was asking about the monocular pipeline and whether that works without sensors, and just confirming that it is pure.
Yeah. So yeah, and then the workbooks we'll go through in a few minutes. We're not gonna, most of you don't have our app, so you won't have sensor data from the phone. That does help to disambiguate things. As I mentioned, we've done some work using SLAM. In the end, it's not made it into the paper because we couldn't quite get the 3D positional tracking accuracy as high as we'd like. And so it can work just fine, especially if you have a still camera, right? If you have a still camera, you got no problems. And in the MOBI data set that we are including in the preprint, that was a still camera. And our root translation errors were on the order of like 4 centimeters or something like that. So we can track position quite nicely if you got a still camera.
We'll get an idea of this in the tutorial as well, but two related questions, one from Aaron Cherian and one from Babak Tati. Aaron was asking about how long it takes to go from recording to process results, and then Babak was asking about um, how long of a video segment do you need to fit the biomechanical model?
Yeah, I mean, so in our standard workflows, we're more of a throughput than latency oriented lab, right? So a lot of times our data is collected by our collaborators and it flows through into our infrastructure over the order of like a week. A lot of that actually just being when people upload the information about this experiment is associated with this person. But you'll see in the workbook we're about to do, hopefully we can go from a video to results in under 10 minutes. The other thing is when we use this system, again, tied into our big infrastructure, right, we'll do the bi-level optimization. So we'll fit all the trials as one optimization approach to make sure that a person has a single skeleton during that, which is not going to be in the notebook. And so, yeah, we can get it done pretty quickly. I think there's a lot of pathways to get it much, much faster. It's just not being a priority for us. We're more focused on accuracy. But I think you can keep most of the accuracy and get the speed up if it was a priority. Oh, and then I think Babak was asking about how long of a recording. We haven't, so a lot of our recordings are on the order of 10 seconds. We've gone up to several minutes. Within that range, it's not been a major issue for us. In particular, as a detail within that implicit function, we actually have positional encoding. So we go from time to a series of sinusoids. And we compute the number of elements we need for that to make sure that the minimum frequency of the sinusoid is like 40 hertz. And we're just basing that off of like, I think it was 40 hertz, maybe 80 hertz. I can't remember exactly. But that was kind of aligning with the numbers I often see in biomechanics papers. We have not tried on the order of an hour. It would probably require changing some of the optimizing parameters. Similarly, we haven't tried on the order of like sub-second. But at that point, I think there'd be a lot of different details.
Next question is from John Popa. He was just noting that adding additional tasks improve the accuracy of your model, and he was just curious whether there are specific tasks that really give you a big jump.
Yeah, so we didn't go through all the permutations. Wrong paper. Why am I not seeing this slide? Yeah, there it is. So I just kind of went and I started with these ones and added diagnosis, assistive device, and falls. And then we added in like the timing-based tasks. So I don't know. I mean, there's obviously a lot of permutations. We were thinking more just add more and more things. And we're starting now, like we have an annotation dashboard for getting to a lot more fine-grained annotation to really start building more detailed motion scripts of what's happening. And I hope it'll just continue to get better, but we weren't trying to figure out what we could strip out with the least devastation. And there's the opportunity to take that biomech agent that can write code to actually create additional feedback to biomech GPT. So there's a whole field of reinforcement learning from verifiable feedback that's kind of been exploding in recent years, and that's definitely on our roadmap.
This is just a quick clarification question from G Chen. I think it's on your plots for the monocular of what
It
is
is, and hang on, I may have
one
to go
L
back to,
and an R. Yeah.
yeah. I'm gonna have to go back to JD and ask that. Oh, it's probably, oh, it's left leg and right leg. Yeah.
Gotcha.
I was pushing away from, I have bad color vision, so I was trying to minimize the color usage there.
Definitely. Um, Next question is from Sasha Portanova. How does your algorithm deal with multiple people in frame?
Hey, Sasha. So the workbook you're going to use doesn't deal with it. So when it's in our whole infrastructure, just like for the multi-camera system, we have that annotation step in our single camera pipeline. And so I'd encourage you to check out our paper on postpipe. So we have this whole database-backed infrastructure. One of the stages in the pipeline is it computes the bounding boxes and then lets you go and say, well, bounding box 3 is my participant, or bounding box 7, or even like they got split, so it's bounding box 3 and 19. And so we do that to actually to have a human review who is the person we want to analyze and annotate it. If there's only one person in view, then you can do it automatically. And I suspect we have enough data now that we could probably train a system to be like, I'm pretty sure this is who they're recording, because normally, you're kind of keeping them centered. There are good algorithms for person re-identification. So I think we could minimize that, and we actually have some internal funding to do just that.